And this session is organized by NASA, and it is on the topic of perseverance, ingenuity, and future of Mars science and exploration, and it will see the participation of many distinguished speakers. So please, if you could take a seat. Please also don't forget that you can engage on our Slido platform and ask questions and rate the questions. And now I give back to the moderator of this session, Pascal Ehrenfreund, the IAF president.
Okay. So, welcome here in person and online to the Global Networking Forum, a panel on the topic Perseverance, Ingenuity, and the Future of Mars Science and Exploration. So, the Mars 2020 mission and its Perseverance rover is now the 5th rover that NASA landed successful on Mars. And Mars 2020 is one of 3 missions that recently arrived on Mars. We have discussed it, and there will be other panels during the Global Exploration Conference. The NASA Perseverance rover will track down traces of earlier simple life forms in the Jericho crater, a region which was very likely underwater 3.8 billion years ago. So 7 scientific instruments are on board the rover, and the aim of the mission is not only to explore the habitability of Mars, but also to collect samples from the Martian surface in more than 40 canisters or tubes in order to return them to Earth for analysis in the framework of a Mars sample return mission. So Perseverance has delivered amazing results already. And I think more than 80,000 images, microphones have recorded the first audio soundtracks of Mars, which probably many of you heard. And the science phase has been kicked off in June. So over the next several months, Perseverance will be doing a lot of exploration on the Martian surface. So this Global Networking Forum panel will discuss Perseverance science and technology milestones to date and upcoming science plans, as well as explore how this mission feeds into future Mars missions, including the Mars sample return mission, and also future human exploration. So before I introduce the panel, I would like to give you a short outline how the panel is going to work. Each panelist was selected to tell a story about the exciting accomplishments of Perseverance, what they hope to discover, and where their discoveries take us in future missions and plans. We are planning to have each panelist speak about 4 to 5 minutes on their role within the Perseverance mission and science. And following the brief presentations, we will open the panel to questions and answers. And as you have been informed, also the audience, remotely and here in person, can interact and pose questions using the Slido tool. And the instructions, I think you can either see on the screen or you will be notified. So the panelists will include Laurie Glaze, Director of NASA Science Mission Directorate's Planetary Science Division; Matt Wallace, Mars 2020 Perseverance Project Manager from NASA Jet Propulsion Laboratory; Ken Williford, Deputy Project Scientist for the NASA Mars 2020 rover mission and Director of the Astrobiogeochemistry Laboratory at NASA JPL; Veronica Pinedo-Gonzalez, she is the MEDA Operation Engineer at the Centro de Astrobiológica in Spain; and Sandra Siljeström is the Mars 2020 mission return sample scientist from the RISE Research Institute in Sweden. So I will give the first word to Laurie Glaze.
Thank you so much, Pascal. And it is just so wonderful to have an opportunity to participate in the Global Space Exploration Conference today remotely. If I could have the first graphic, please. We're here to talk about primarily the Mars 2020 Perseverance rover. And if the first graphic is showing, you can see on this graphic the broad collection of spacecraft and landers and rovers that have and that are participating in exploration at Mars today from the global community and that we see coming in the future. And there, as you see, participation from multiple agencies around the globe, including NASA, ESA, Indian Space Agency, JAXA, Russia, and China now, of course, now joining us, and the United Arab Emirates as well. The NASA program for exploration of Mars over the last 20 years has really taken a stepwise approach to trying to understand how to best look for life if it ever existed on Mars or if it is there today. The first phase of that exploration was focused on following the water, trying to understand where water may have persisted on the surface of Mars and when, at what time periods in Mars's past was liquid water present at the surface of Mars. Then the next phase was trying to go into those areas where we saw evidence of water over time and explore the habitability of those areas. Were all of the ingredients present that could have supported life on Mars at some point in the past? And then with all of that information, that helped to guide us in our decision to land the Perseverance rover at Jericho crater on Mars this last February. And now we are well prepared to start seeking the signs of life that may be preserved and saved within those rocks on the surface. And if we can go to the next graphic, please. These are the primary objectives of the Mars 2020 Perseverance rover. First and foremost, our first objective is to really understand the geology of the landing site within Jericho crater, to understand the history of all of the processes that have occurred within that crater over the last 3.5 to 4 billion years, and trying to set the context for what that environment has been like. The second objective, as I mentioned already, is very focused on the astrobiology of that landing site, understanding the environment, whether or not it contains the right ingredients for life to have existed at some point in the past, and potentially even looking for signs of past life that may have been present in that amazing river delta that we find in Jericho crater. And Ken Williford is going to be speaking much more to that science and that astrobiology that we have, that we will be looking for with Mars 2020 Perseverance rover. And then all of that is going to help inform how we decide and where we decide to collect specific samples of the rocks and soil that we can bring back to Earth with the Mars Sample Return mission. And Sandra will be speaking to us more about how we make those decisions of which rocks and soils to collect and what we will do with those samples when we bring them back to Earth. Sandra has an important role that bridges between the Perseverance rover and Mars Sample Return to help us be prepared to analyze those samples when they come back. And then we have another goal here, which is actually preparation for human exploration at Mars with several experiments that do technology demonstrations to help us make sure that we're ready for human exploration in the future. And if I can have my last graphic, please, to just quickly show the broad array of different experiments and instruments that we have on the Perseverance rover, mostly focused on science. You can see lots of international participation on this rover. It's truly an international rover. And then several technology demonstrations I just want to highlight quickly. First, of course, the MEDA instrument that is provided by Spain. And of course, Veronica will speak more about MEDA. It is a weather station that not only does science, but also helps us better understand the environment on Mars for future human exploration. We also have the Moxie technology demonstration, which has already generated very pure oxygen during 2 experiments so far on the surface of Mars. That very pure oxygen in this experiment demonstrates the ability to use the carbon dioxide atmosphere present on Mars and convert that into breathable oxygen that could be used by astronauts and potentially also fuel. Finally, I just want to highlight very quickly the Ingenuity helicopter that you can see towards the center here in this graphic. The Ingenuity helicopter has been an amazing technology demonstration. It has flown 5 successful technology demonstration flights that have, for the first time ever, demonstrated powered and controlled flight on any other planet in the solar system. And it has now also conducted 2 successful flights in the operational demonstration mode, where it is flying along with the Perseverance rover and demonstrating just how such an aerial asset, such a helicopter, could be helpful in augmenting the science return of a potential future, either human mission or robotic rover mission. And so with that, I want to hand it over to Matt Wallace, who's going to speak more about the very exciting landing of Perseverance rover and where we are today with what has been accomplished so far.
Thank you, Laurie. Matt?
Science and technology mission, which Laurie just finished talking about, we of course had to safely get onto the surface of Mars, and that's never an easy thing to do. If we go ahead and bring up the first graphic. Oh, back one, please. Thank you. There we go. So in the background of this image, you can see Jericho crater, which is a scientifically fascinating location. You're going to hear more about it from the scientists on the panel. This ancient crater lake holds a lot of fascinating targets scientifically, but when we look at this as engineers, unfortunately, what we see is a lot of danger. There's a lot of vertical relief. There's crater walls. You can see the escarpments. There are sand fields, boulder fields. So this is not an easy place to get down and into. And in fact, this particular target is one that we have tried on some of those previous Mars rover missions to get to, but it's just been deemed too dangerous and too difficult. This time we were carrying some hazard avoidance capability, and so Perseverance decided to go ahead and head to Jericho. And the way we get there is an exciting set of activities. We arrive at the planet moving at about 13,000 miles an hour on a ballistic trajectory. The heat shield will slow us down to about 1,000 miles an hour when we deploy this large supersonic 70-foot parachute traveling at Mach 2. Once that slows us down to a couple hundred miles an hour, we'll fall out of the back shell. The big main engines on the descent stage will fire up and hopefully carry the rover the rest of the way down to the surface, executing the sky crane maneuver, which is part of this mission's terminal descent activities. So that's the background, and I thought what I would do is go ahead and show you how this played out on February 18th on the next chart.
Propulsion, go. EDL phase lead, go.
We have deemed Perseverance ready to execute entry, descent, and landing on her own.
Confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second, about 120 kilometers from the surface of Mars. It will start controlling its path to the landing target. Parachute has deployed and we are seeing significant deceleration. The heat shield has been separated. Perseverance now has radar lock on the ground. The back shell has separated. Sky crane maneuver has started, about 20 meters off the surface.
Tango Delta, nominal.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
Thank you very much. Go ahead and go to the next chart, please. So February 18th was obviously a very exciting, terrifying, and gratifying day for the entire team. And as Lori mentioned, it's a very large team, a couple thousand people at JPL, thousands of vendors around the country, and a lot of international contributions and participation as well. So a big day for a lot of people on the Perseverance side of things. Since we've gotten to the surface, we've been busy, of course. As mentioned, we've taken tens of thousands of imagers that we brought back to the Earth. This first one in the top left corner is our first selfie. And not only is it a picture of the rover, but also you can see in the background Perseverance, which we deployed shortly after landing. And on the top right-hand side, you can see that Perseverance returned the favor. And on one of its flights, I think it was flight 3, it managed to get an image of the rover on the surface in that top left corner. And so we've now imaged each other. But we've been busy flying the helicopter, as mentioned before. We've now flown 7 flights, both technology demonstration flights as well as the operations demonstration flights, which Lori mentioned as well. And you saw a video in the lower right corner. In addition to that, we've been checking out all our engineering systems. The vehicle's very healthy. It's performing extremely well. The science instruments, which Lori talked about, have also checked out well. You can see a picture of the robot arm in the lower left side. That's the arm that we'll use to start sampling, which we hope to do in the next month or so at Jericho and start that key science surface mission. So things are going well so far. We got a lot of work ahead of us, but it's been a great mission so far. And I'll go ahead and close out and hand off to the next presenter here.
Do we have a change of speaker now? We thank you for your wonderful video. It was amazing. I'm sure we want to see that again. And I think we are continuing now with Ken Willeford. Am I correct?
Yes, I believe so. Yeah. Okay. Hello, everyone. I'm Ken Willeford, Deputy Project Scientist for Mars 2020. And thanks, Matt. It was fantastic to see that video again. So exciting, brought back such great memories. We're all still very much excited as the science mission begins to unfold. So I'm here to talk to you a little bit about that today. And thanks for the first graphic. Yeah. So I chose this image because this just brings the point home that the science mission is underway. So this is our robotic arm. It's a picture taken from one of our front HazCams or hazard cameras that the rover uses predominantly for its autonomous navigation and ultimately hazard avoidance capabilities. But it also can take documentation images like this of science observations that we're taking on the surface. And in this case, you can see several interesting things. So first of all, the instrument that's pointing down sort of in this direction at the rock target in front of the rover there is Sherlock. And Sherlock has two primary components. It has a laser spectrometer that does fluorescence and Raman spectroscopy. This is our primary instrument for detection of organic matter, and it also provides some mineralogy for us. On the opposite side, so pointing up to the sky, you see the Pixel instrument there. And a Pixel is an X-ray, a fluorescence spectrometer that provides elemental chemistry of rock targets. And one thing I wanted to point out here that is distinct about these instruments compared to instruments flown on previous Mars missions is that these instruments make maps. And this is crucial to the astrobiology objective and the geology objective that you heard Lori talk about. So as you heard earlier, our objectives are to land in Jezero Crater, start to understand the basic geology. How did the rocks that we see around us form? How were they altered after their formation? Then we take the next step in a way that's very similar to the previous Mars rover Curiosity, where we investigate the habitability of the environment that's recorded in those rocks. We ask the question, could that environment have supported microbial life in the distant past? But here's where we take the big next step forward for Mars surface exploration, and we are directly seeking the signs of ancient life. And in order to do that, we use our cameras, of course, and we keep our eyes peeled for, I'll hold this up to the camera, hopefully you can get sort of a view. You see these concentric rings in this rock. This is called a stromatolite. And the rings are ancient layers of a microbial mat. So this is about a 2.7 billion year old stromatolite from Western Australia. And these wrinkly layers here show you, layers of pond scum, we might call it, layered one after the other with sediment in between, piling up over time, and ultimately fossilized and preserved for billions of years. So we'll be on the lookout for structures like that, but shapes alone are really not enough to give compelling evidence of ancient life. And so this is where we want to use those mapping instruments, Pixel and Sherlock, to scan a beam across the surface and look at how the chemistry of that rock target varies in space. So this is our basic approach. We look for lifelike shapes that occur together with lifelike compositions in these rock targets. So if we can see the next graphic, please. This is an animation showing you what was really a focus test. So this will loop, and you'll see this is the Watson camera, which is part of the Sherlock instrument, being deployed closer and closer to this rock target. And I thought this was thematic as well. Of this is our basic approach. We just look at science data across all various scales, from the orbital to ultimately the microscopic. But this turned out to generate very beautiful images. And in the final image, it's hard to see, but you can go and check it out on the website if you like. Up in the top right, you'll see tiny holes generated by the SuperCam laser instrument. So next slide, please. Okay, this is my last image, and this is just showing you an image beautiful image taken from the Ingenuity helicopter to point out how the helicopter demonstration is actually providing some great science value. And you heard earlier that our first science campaign is now well underway. And this is an image of the main area that we're exploring that we call Sita. And Sita is a word in the Navajo language that means among the sands. And as Matt pointed out, this is one of those main hazardous areas in Jezero that led to some challenges that we had to work around for landing. But we're going to skirt the contact or the boundary of this Sita region with all these sand dunes that you can see. And in between the dunes, we'll work to drive the rover in between the dunes and access those flat-lying rocks that you see there. We call them the paver stones, and a rock like that is likely to be our first sample. So these rocks that you see here are likely among the oldest, if not the oldest, materials that we'll be able to investigate during our exploration of Jezero Crater. So thanks. Now I'll pass it to Veronica, who can tell you some more specifics about the meta investigation.
Thank you very much. So I'm calling now Veronica. She's the MEDA operation engineer, and she will tell us something about the MEDA instrument, I guess.
Yes. Hi. It's a pleasure to be here today introducing MEDA in this panel. MEDA is the Mars Environmental Dynamics Analyzer on board of the Perseverance, and is included in the objectives of the preparation for humans. And the reason to be included in this objective is very important to know, to characterize the environment in Mars, right? The most obvious reason of this characterization is, well, if the people will be living for some months or years on Mars, we need to know how is the ambient, and to be ready to live there. Not only the present condition of the ambient, I think it's important also the past, and to know the evolution, why the planet changed a lot until the current state. And it's important to know if that evolution continues and how will be the condition in the future. Okay, thinking in that humans in Mars. Other important reason of this characterization, the preparation for humans, is when humans will be living and working in the planet, will be very important the in situ resources utilization, and also the necessary instruments to use that resources. So it's important to know how the conditions in the environmental condition and the components of the atmosphere can affect that instruments and that resources. I think the best example is, for example, Moxie. Moxie is the other instrument included in this objective, the preparation for humans, is the generator of oxygen. Well, we can think how the dust can affect to the instrument, for example, in the filters to get the air to generate the oxygen. So this is only one example, but I'm sure when people will be in the planet, we will need a lot of these resources and instruments, and it's important to know how the ambient can affect to this, okay? And also, well, Matt commented the complexity in the entry, descent, and landing phase. Not only in this phase, in general, in the engineering, it's also important to know the conditions of the ambient, because that can affect, for example, in the different condition can affect to the density of the air, and that, for example, can affect to the descent. And this is especially important when we are talking humans on board of the spacecraft, right? So this is some of these reasons to be included in this preparation for humans, and why it's important to know the environmental. Okay, next slide, please. And for this, we have the instrument MEDA, that's Mars Environmental Dynamics Analyzer. This is a suite of different sensors allocated around the rover. We have in the mast, for example, we have the wind sensor. We have 2 wind sensors to cover the different angles. Okay, we have also in the mast the humidity sensor and the thermal infrared sensor to get the radiation information in the radiation in the low atmosphere and also in the surface. In the inside of the chassis of the rover, we have the pressure sensor, which is connected to the top of the deck with a tube to acquire that data, but to be protected at the same time. And the last of the sensor or MEDA is the radiation and dust sensor. This sensor has different photodiodes and different angles to cover more field of view. And with this sensor, we will be able to analyze the dust, the opacity, the dust size, distribution, And that will be important for the reason we show in the previous slide. In this sensor, in the radiation and dust sensor on the top, we have the SkyCam. This camera is viewing the sky, and this will be used also to know that for the analysis of that dust will be very important to be that images, analyze that images together to the radiation and dust sensor acquisitions. So with all of this suite of sensors are interesting, the sensor individually, but I think it's most important to have all the acquisition together and see and know the general condition of the environment. Some things we will try to get with this data will be to support the validation of the different models, okay, and also to know the environmental in the microscale and also in the mesoscale. And that is my brief introduction at our instrument. Thank you. I think the next is Sandra.
Thank you very much, Veronica, for telling us about the environmental analysis. And the last speaker of this distinguished panel is Sandra Siljeström. And she will, I think, also talk about returning samples to Earth from Mars.
Yes, so I will talk about, so I'm a returned sample scientist, so I'm part of a group of scientists that was brought on to this sample because one of the very important objectives, as was pointed out earlier by Laura, is to collect samples. So in this first slide, you can see that on the left there, you see a model of the sample tube that Perseverance is carrying on the belly. And you can see, so in A, you have the sample tube, and in B, you can see the drill cores, one of the drill cores we hope to drill. And so the drill core is roughly 1 decimeter. So we collect a number of these different drill core up to around 40 samples and to collect. And these, so we'll drive around, collect these samples, and the idea is then to later put these sample tubes with the drill cores and also probably a regolith sample in different caches that can later be picked up by future Mars sample return. So if we can go to the next slide. So why is it so important to return samples to Earth? So even though we have a great set of different instruments on the Perseverance to characterize the geology and the potential for life on past life on Mars, it's still never going to compete with the capabilities we'll have on Earth, where we have different kinds of instruments that will never be small enough to be brought to Mars. So, for example, like the extreme example is, of course, the synchrotrons, but also other more advanced instrumentation. There's also this capability of doing much more complex sample preparation. So we can prepare, for example, thin sections, we can grind the samples and extract with solvents, etc. And also combine these different techniques. And also it's not limited to the particular instruments we have at the moment, but we can combine many different instruments and also instruments that might not exist today. And though we have some samples from Mars today in terms of Martian meteorites, the great thing about these collecting these samples is that we get all this background information from the instruments on the rover, and this will inform what kind of analysis we'll do on these potentially future samples, and these samples will know exactly where they're coming, because context is everything when you're looking for trying to understand the geology of Mars, but also trying to understand if these samples actually do contain life. Because even on Earth, it's quite complicated to prove that you have very ancient life. And if you bring the same problem to Mars, this is of course even more complicated. To have all these capabilities will greatly improve the chances for us to potentially find these potential future life. So if we go to the next slide. So this slide I'm showing, so this is a geological map of different geological units and different lithologies in the Jericho crater. So you can see I put an arrow there in black, which says we landed here, and it's actually right next to this green structure you see there, where it's pointing to the Seda that Ken was mentioning. And so you can see in this slide there's a range of different lithologies we can sample, and many of them are definitely susceptible to potential habitats for life, but also, if not, maybe not present life, it could also be a great place where you have preserved ancient life, especially. So we're at the moment at the crater floor next to this Seda structure, and the idea now is to the next couple of years drive towards the delta and collect these, and these are some of the different samples so that we have within, for example, the delta, so which was one of the reasons that Jericho was chosen. You have, for example, several different lithologies, especially the delta thinly layer, which is might be a great preserver for organics, one of those biosignatures we're looking for. So there's a number of different interesting lithologies that might answer not just questions about potential past life, but also about the general geological history of Jericho crater and Mars, including also dating and get better dates for different events of those things that happen in Jericho, but also on Mars. So that's all from me.
Thank you very much, Sandra. I think we are coming now to the Q&A because we have only 17 minutes left. But I want to thank you all because I think this is an amazing insight, into the Mars 2020 Perseverance project, because we look, of course, at the press releases and we see the main results, but it is really very important to understand, how difficult actually the landing is, and how complicated actually the way is, how you are gonna sample now, and how you are actually, going to explore a 4 square kilometer patch of crater floor. That is really something which is quite complex, and I think what you explained to us is only, a percentage of what actually Perseverance actually does, because there are still a lot of other experiments, and there are a lot of new firsts, like Moxie and like Ingenuity, which made a lot of headlines, of course. And so I want to thank you, because I think it, this session will be on our website in the Global Networking Forum, so people can look at and switch it on anytime, the members of the IAF. And it will remain a really important documentation of where you are just now starting at the science phase. So I want to thank you for this overview. And there are a few questions which come in. They are quite heterogeneous, but I wanted to start, and of course it is the best that you select who is going to answer that question. If nobody wants to answer that question, that's a problem. But there is a question about the geological properties between the Perseverance landing site and the Curiosity landing site. What are actually the major differences? And a more sophisticated add-on question is, when you actually examine the area, do you actually then are able to make a Mars analog with the data which you have gathered by the rover, and then do additional experiments on Earth with this analog?
I could take that one, if you like.
This is Ken. Ken, are you?
Yes.
Yeah.
Yes, good. So it's a great question. There are certainly some similarities between the Curiosity landing site and the Jericho landing site, in that we think both landing sites once had a lake. There are certain minerals that are present at both sites that are sort of commonly distributed on Mars. But you asked about the differences, and a key difference is how beautiful the orbital expression is of what we call the geomorphology, the shapes of the rocks. So it's so abundantly clear to us, given the distribution of geologic features, that river channel coming in, the beautiful delta exposed inside the rim of the crater floor, etc. So we have a much easier time in Jezero than we do at Gale Crater, understanding even from orbit where all the different sub-environments would have been. And we can then base our exploration strategy. This gets to Pascal's, the challenge she indicated about exploring this giant area in a limited amount of time. Having that distribution of geologic features so obviously pointed out from orbit really helps us plan out that exploration very well. One other very key difference between the landing sites is that we have evidence from orbit of carbonate minerals in Jezero Crater, and this region, the region where Jezero is the greatest concentration of carbonate minerals known on the surface of Mars. And this was a major scientific draw to this region, because carbonate minerals on Earth, this sample I showed you, is made of carbonate minerals, calcium and magnesium carbonate. These minerals are often associated with biology on Earth, not always. Coral reefs are made out of carbonate minerals, for instance, seashells. But so we know they're very good at preserving biosignatures. But even if Mars was never inhabited, a carbonate mineral represents the crystallized intersection of the atmosphere, the solid planet, and liquid water. That's where carbonate minerals form. So they preserve that interaction in what we call the critical zone, and they'll preserve a record of climate through time and many other things in those carbonate minerals. So that's one of the things we're most excited about. And then I'll just give a very simple answer to the second part of the question. Can we use the rover data to make soil simulants? And it's an emphatic yes, absolutely we can. And there are plenty of people working on that. We can't hear you, Pascal.
Sorry. I just was on mute. What is the lifetime of the rover staying on Mars? And I think this is a very difficult question, because we know from previous missions that they have been extended above the lifetime which was anticipated. But is there any kind of prediction which you can make?
I can probably answer that. So the Mars, the primary surface mission, is designed to be 1 Mars year, which is essentially equivalent to 2 Earth years. But we have qualified the hardware for 1.5 Mars years, which is about 3 Earth years. Now, having said that, as you mentioned, Pascal, this is a system like our previous vehicles that's really designed to last. It's and once you get past those first set of sort of infant threats to the engineering systems in particular, there's a very good chance that the vehicle will last quite a bit longer than that. So we're hoping and planning for a very long surface mission, but the hardware qualification is about 3 Earth years.
Great, and one can only hope that it is as long as other Mars rovers. So there's a question I actually have, because I think it is also a question of interest for many people, and that concerns the cache in the of the samples in the different tubes and canisters. So we read, and you have been explaining, that there are more than 40 canisters which might be filled, but there might be some hiccups. And how do you actually really select the best places, and what do you do actually at the end when you have just to select a few? You mentioned that there is a sample return worthy cache system or concept. And I think it's for us quite interesting, will all 40 canisters be brought back? Will you actually then select a few? And how are you really sure that this is the best material for a sample return mission?
Do you want me to answer this question?
Yes, Sandra,
Yeah,
would be great.
And then if there's something I can add, go ahead.
So the idea, so it's actually 38 samples that we can maximum collect, and in terms of the cache, it will be probably several different caches. It's not clearly decided, and it might change due to reasons also due to the Mars sample return mission, how that goes. So, but the idea at the moment is to have two different caches. One cache will be put down after this 1.5 year that Mike was mentioning, and then hopefully if Perseverance work, will collect another set of samples. So the whole 38 won't be brought back, because I think there's a limit also on the Mars ascent vehicles, around 30 or something. So we won't get 40 samples back. We'll get roughly 30 maximum. And it depends on the number of caches and how everything works out. And in terms of selecting the samples, we do the best we can do with the data available. So we'll collect carefully. So this is one of the most important, is not just to collect the samples, but also collect all the information we need, starting with these overview images taken by the cameras down to chemistry from afar, and then chemistry close, like Pixel and Sherlock. And all this together weighs together also with terms of the different objectives these samples we want to answer with those. Because, we want to answer many different questions. There's many interested scientists around the world. So this is part of the job we have as a return sample scientist. It's also take these in account. And this is, of course, these samples are chosen by the whole Mars 2020 science team. So all their expertise will go into. So we have some ideas where we want to go and where we want to sample, but this is, of course, going to be affected what happens on ground. So, Lori?
Yes, I can add a little bit to that. I think Sandra described very well the important role that the international team of sample scientists will play in helping to interpret the remote sensing information that we are gathering with the Mars 2020 Perseverance rover, and helping to decide exactly which samples to collect and which to place on the ground in a cache that could be then retrieved by the sample fetch rover that would be carried on the return lander, or potentially held on the Perseverance rover that could also deliver samples back to the return lander. So that is an international participation in trying to determine those best samples. They will be working very carefully with both the Mars 2020 team and the Mars sample return development team to make sure that we have the capability and we're planning into the capabilities of that sample return mission, the ability to get those samples, to select the best samples to bring back. And so, as Sandra says, there will be potentially some decision points where we want to put some of the samples onto the surface on this cache. And that will be, the decisions will be made at that time, trying to look at the samples that we have available and where we still want to go to make sure that we are putting down the best collection or a reasonable representation of samples that we would want to bring back. So there are lots of different factors that will play into that decision, and it's a decision that will be made by a team of people that will then make recommendations to NASA and ESA on how and where to place the samples.
This is very interesting because it adds really a degree of complexity to the mission when you actually, perform science and tasks for a next mission, and you actually have always to involve a lot of scientists, which have all probably not always the same opinion. So I can imagine that this is quite a complex but a very exciting task, because on a Mars sample return mission we all work already for decades. And we will be very, very happy that it actually finally materializes. I have also a question, because we have also from the chat something related about the Moxie experiment. If you could just say a few words. You mentioned that 2 experiments have already been performed and rather pure oxygen. And if you could just describe because we have an interdisciplinary audience, not always, completely familiar with the topics of in situ resource utilization, if you could just explain it in a few words, and what those preliminary experiments or the first experiments actually mean.
So I don't know, Matt, do you want to take that first?
Yeah, I can say a few words. I think we actually have executed 3 Moxie experiments as of last time I checked. So it's an exciting technology, obviously, to be able to produce oxygen from the carbon dioxide Martian atmosphere. It uses a ceramic electrolysis dissociation of the carbon dioxide to create that pure oxygen. And we've been running the experiment at different times of day, under different conditions, at different oxygen generation rates, just trying to get a good understanding of how the technology performs over the different environmental factors. So far, each experiment has done extremely well. It's right on the predicts as far as oxygen purity and oxygen generation rates. The system's performing very well. We nominally would like to get 10 to 15 of these experiments done during the primary mission. We may get more, because the system's working well, and we are finding places to insert these experiments into the operational activities. It requires a lot of power, actually, to run the experiment. It creates a lot of heat. And so we have to pick certain points during the operational cycle to do it. But so far, Moxie has performed as expected, and it's an exciting technology to be using at Jericho.
Thank you very much. I have a final question. And then we have, more or less slowly to close the session. We have a question from the audience. What would happen to the samples after they return in terms of research and safekeeping?
Yeah, so why don't I take that one, Pascal? So there are, of course, already many plans being developed now, thinking about both of those aspects, making sure that we, of course, keep the samples contained and safe when they are first returned to Earth. Returning a sample from Mars is categorized as a restricted sample, meaning that we must keep it safe until we can demonstrate that it is safe. And so we are wanting to make sure that we will keep it contained. Once it has landed, it will land in the Utah desert, Utah of the United States, and be contained. But then we also want to quickly be able to determine whether or not there is anything harmful in the sample, and hopefully be able to release those samples either by determining that they are safe or by sterilizing the samples. And then we can begin a lot of the analysis in earnest. There will be analyses conducted even while the samples are under containment. We'll make sure that we are characterizing the samples well and preparing to release them. But the big plan, of course, is to make those samples available to the world, to the scientists of the global community, to analyze and study for many, many decades to come.
Wonderful. We want to really thank you, the Perseverance, Ingenuity, and Mass Sample Return team. I think it was a wonderful journey, beautiful images, and perceptions. What's gonna be, what's gonna happen on Mars in the next, hopefully, 3 years. I have one very small question. Is this video which you showed, is it on the website of NASA or JPL? Or?
It is.
Yes, if you mean the landing video is definitely on the website.
We will link it, yeah. We will link it from the IAF because it's really wonderful and shows the enthusiasm also for the next generation. We wish you all the best for the mission. I know that it will be very, very time-consuming and exciting for all the team members, and this is a big team. We wish you all the best for the next months and all years, but we hope we hear an update from you in Dubai about the news results, and we thank you so much for giving us all this information about Perseverance.
Thank you.
Thank you very much. And I thank the audience here and the audience online. And this session will be is videotaped and will be on the website of the International Astronautical Federation for watching. And all the best to the Perseverance team. Bye-bye.
Thank you all for being with us. We will continue shortly after quick reconfiguration of the stage with another most interesting Global Networking Forum session on the topic of lunar surface infrastructure organized by Thales Alenia Space. So be with us in about 3 to 5 minutes. We'll start. Thank you.